You have seen now the generative AI is no longer just a buzzword. It's been our daily life, part of our daily lives, right? Many company leaders say they have seen clear benefits from using GenAI, especially in making their work more efficient and keeping customers happy. This shows that GenAI is a valuable tool that brings real return. It's now a key part of our business plan and for the future. I am Saloni Narang. I am co-founder of Kubesimplify, Docker captain, and a CNCF ambassador with 12 years of experience in IT.
My name is Aman. I'm a founder at Welzin. It's an AI firm with 12 years of experience in data science.
So the agenda for today's talk will look like we'll talk around GenAI revolution, transformers to LLMs, DR in K8s, Kubernetes, multi-NUMA in Kubernetes, why inference is hard to scale, vLLM in AI trend, scaling inference on Kubernetes with vLLM, vLLM architecture, and then there will be a demo time. I hope it works. When we think of AI, especially with all the buzz around GenAI and LLMs, it feels like something brand new. But AI isn't new. It's just finally usable at scale. What's different now is that Kubernetes has emerged as the perfect backbone to deploy and scale these intelligent systems. And tools like vLLM make LLM inference efficient enough to actually power real-world applications. So no, AI isn't a revolution out of nowhere. It's more like a rocket that's finally launching after 60 years of countdown. AI is increasingly embedded in everyday life, from healthcare to transportation. AI is rapidly moving from the lab to daily life. In 2003, the FDA approved 223 AI-enabled medical devices, up from just 6 in 2015. On the roads, self-driving cars are no longer experiments. Waymo, one of the largest US operators, provides over 150,000 autonomous rides each week, while Baidu Affordable Apollo robo-taxi fleet now serves numerous cities across China. Now talking about what generative AI actually is. Generative AI refers to the type of AI that can generate new content based on the data they have been trained on. It includes foundation models like GPT for text generation and stable diffusion for image creation. Generative models such as diffusion models and GANs are developed for high-quality, diverse, and efficient output generation. These technologies power a wide range of applications across industries, improving workflows and enabling innovative solutions. Challenges include computational demands and data quality, while benefits include content creation, efficiency improvement, and new data analysis methods. So now the models have become multimodal. What does that mean? Now you can give input in terms of text, images, audios, code, and you can get output as well in the terms of text, images, audio, and code. These are some of the main examples of generative AI. So now, for text generation, we have Claude, Gemini, Llama. Diffusion and image generation, we have Stable Diffusion, Midjourney, DALL-E. For audio, we have Whisper, Meta, etc. And for the video generation, we have Sora, Veo, Runway. I'm sure you must have used some of these.
Now, if you guys are active in the AI/ML space, you must have all seen this architecture diagram. So this architecture diagram is about the transformer architecture. So this architecture is the baseline for the LLM models, right? Now, this architecture talks about the self-attention mechanism based on an encoder and decoder mechanism, or encoder-decoder transformation, right? Now, the transformers are actually the neural networks which are based upon the self-attention mechanism. Now, what is this self-attention mechanism? It's a simple mechanism which tries to understand the sequence of words and tries to understand the words and figures on which to give attention. Now, this mechanism then becomes the backbone of a LLM model. Now, LLM model is simply a large language model trained on a large corpus of data, which works on the self-attention mechanism, which again is the backbone of a transformer model. So all the LLMs work on this same transformer model, which is the same, again, self-attention mechanism model. So this is the only paper which was written by the Google guys around 2017 or 2018. And based on this paper only, the transformer architecture came, and then on top of this architecture, self-attention mechanism came, and then on top of this architecture or this algorithm, LLMs were developed. So, yeah.
So OpenAI, the AI research lab behind technologies like GPT, ChatGPT, DALL-E, relies on Kubernetes to manage the vast infrastructure required to support their large-scale machine learning workloads. Kubernetes is a key part of OpenAI's ability to scale its operations efficiently across both cloud and bare metal environments. As you must have seen yesterday, Janki Ram also presented that how Kubernetes is the backbone for OpenAI. So Kubernetes is the top orchestration system, as we know. It's already in place, and now with the organization banking on Kubernetes to run AI workloads makes more sense, right? So let's talk about something that's changing the game for AI workloads in Kubernetes. So let's talk about DRA. What DRA is, it's dynamic resource allocation. Traditionally in Kubernetes, we used to pre-allocate GPUs, FPGAs, or high-performance storage to pods, even if they don't need it all time. That leads to waste, over-provisioning, and a frustrated scheduling experience. DRA flips that model. It lets your pod request specialized hardware, like a GPU or a fast NVM volume at runtime, when they actually need it, not before that. Think of it as an on-demand resource allocation for AI, similar to how serverless works, but for hardware accelerators. In the world of LLM inference and GenAI, this kind of dynamic flexibility is exactly what we need to run smarter and more efficient workloads. Moving on to DRAnet, this is something done by Google. As AI workloads explode in complexity and diversity, Kubernetes scheduling needs to evolve. And that's where DRAnet by Google comes in. DRAnet is a new way to handle high-speed networking like RDMA for AI and ML workloads in Kubernetes. Instead of using complex plugins and custom scripts, DRA lets you set everything like off eBPF or tuning network cards right in your Kubernetes YAML. It's fast, it's secure, and now in beta. Built using DRA, Dynamic Resource Allocation feature. It's now open source and super lightweight, under 50 MB, and runs safely without any extra tools. If you're working on high-performance AI or HPC workloads, DRAnet can simplify your networking setup. Now coming to NUMA. NUMA stands for Non-Uniform Memory Access. As AI and data-intensive workloads continues to push down the boundaries of compute infrastructure, understanding how Kubernetes schedules pods in relation to the underlying NUMA topology becomes very critical. NUMA, or non-uniform memory access, refers to how CPU cores and memory are physically being structured in multi-socket machines. Each socket has its own local memory, and accessing memory outside that socket is slower. In Kubernetes, if a pod scheduled without NUMA awareness, it might get placed across cores that span multiple NUMA nodes, causing cross-socket memory access, high latency, and cache inefficiency. This is especially painful for LLM inference, training jobs, and low-latency AI inference, where performance drops just from poor core memory locality.
So till now, we have seen what is GenAI, what are LLMs. We discussed about what is DRA and how NUMA is solving the problem on Kubernetes, right? Now let's come to the LLM inferences and inferencing on AI, right? Now, most of us are running all these LLM models via POCs and MVPs. Very less people and very less teams are actually building products at scale and making it production ready, right? Now, in production, LLM inference is different. It's not something regular, like a regular production, right? Now, in production or at enterprise level, LLM inferences are bottlenecked by majorly two constraints. These two major constraints are the GPU utilization, the GPU underutilization, and the next one is KV caching. Now, what is KV caching? In case of KV caching explosion, what happens is the LLM inference does not scale like a traditional web workloads because of the KV cache. Now, when constant requests are coming from the users, every sequence means a different token level history. And we need to store every token history in the form of key value pairs. And that multiplies very fast in an exponential rate when hundreds and millions of user requests comes in parallel. So this is the one bottleneck, which is kind of the major one in case of LLM inferences. Now, the next bottleneck is the obvious one, GPU underutilization. In the space of LLMs and AI, there's a scarcity of GPU, and we all are GPU hungry, right? Now, in real-world requests, again, the user requests come with variable lengths. The length of prompts, the token size, they vary from a few hundred words to a few thousand. These days, we have even reached millions of prompts, right? Now, these can stop at any token. The user request can be stopped at any token. Now, how do we manage this? In a plain vanilla algorithm or in a plain vanilla batching algorithm, what we do is we simply continue from where we left. But in case of LLMs, we cannot do that. When the user has given an escape or has stopped the prompt, we cannot start from the beginning, right? We have to start from where he or she left, where the user left. So this leads to GPU underutilization because a lot of prompts are dropped middle way, and because of that, the cores of the GPU stay idle. They're not used to the full capacity, and the GPU also is not earning its cost, and we are wasting the free resources available, knowing the fact that GPUs are already so costly, right? Now these two problem statements become the foundational points for vLLMs. These are the two problem statements because of which vLLM came into picture, and the core architectural information also came from these two problem statements. The first one is blockwise memory management to maximize the KV caching efficiency, and then the second one is to prepare a sophisticated batch scheduling method which can take this load at scale in real time. The traditional batch schedulers will not work here because in case of traditional batch schedulers, the number of requests could be a few hundreds or few thousands. But in case of enterprise at scale, we are talking about million requests in parallel, which may or may not be dropped. So that is where the vLLM comes into picture, right? So here we can see that vLLM is kind of a hype in AI field, right? From the user perspective, we only know ChatGPT, Gemini, and all these LLM tools. These are quite in hype in the user space. But what about the developer space? In developer space, we have seen that vLLM is the one which is in the hype. So you can see here from 2024 onwards, the red line shows the vLLM trend. It is trending. It is even more trendier than the ChatGPT and other such models, right? Now, vLLM is a simple open source inference engine which is designed to run large language models efficiently at scale and in parallel to perform model serving efficiently and in an optimized manner. Plus, vLLM also helps to utilize the GPUs efficiently, right? Now, how we do that, we'll discuss in later slides, but vLLM makes serving faster and more memory efficient as well, which is important to handle lots of parallel requests and the rising costs of GPUs, right? Okay, so we already spoke about what are vLLMs and what is Kubernetes and how these two are integrated together. Now, both Kubernetes and vLLM work in tandem. They work closely together. We put a layer of vLLM on top of Kubernetes architecture, and then we get all the output of model serving in an optimized fashion, right? Now, we know that Kubernetes is great for managing GPU clusters and CPU clusters, scaling pods up and down, and then abstracting the bare metal hardware layer, right, with a software layer on top of it. Now, vLLM is a tool which is designed to run LLM models in parallel and efficiently on top of this Kubernetes layer to get fast responses for the user prompts, right? This combination of both Kubernetes and vLLM lets the AI teams deploy all their models at scale and manage LLM endpoints just like OpenAI endpoints on their cloud platform or on-prem platform, or on their hybrid environments, right? Now here we can see that both these tools work in tandem. For example, Kubernetes manages the clusters, vLLM layer helps in serving the model at scale. Scaling is taken care of by the Kubernetes part, and inferencing multiple models in parallel is taken care of by vLLM layer, right? So the user can infer using ChatGPT or Gemini or Llama, any model in parallel. So all that is taken care of by vLLM. Now, let's talk about the features, the top features of a vLLM system. The features, again, arise from the same bottlenecks, that is KV caching and GPU underutilization. The features are similar to any other parallel model serving layer, just like Seldon for the cases of regular models. Here also, the first feature that is required is high throughput and the fast inference, because nobody wants to wait for even seconds to get the responses. We are so impatient these days that we want the answers in just seconds, right? So high throughput and fast inference is the first feature given by the vLLM. How we do it is by doing efficient KV caching. The next feature is the memory efficiency. Memory efficiency is given by a concept called paged attention. Now, I'll talk about paged attention again in the later slide, so I'll park it for the next slide. The next feature is continuous batching. So here also we know that there are millions of requests coming in parallel from the users worldwide, right? Now, how do we do that? Again, we have a sophisticated batching system which will batch all the requests into a single batch and then pass it to the GPU. Now, this way, if we pass hundreds of requests in a batch to the GPU will not be underutilized. It will use all its cores, and we will be able to reap maximum benefits from the cost of the GPUs that we pay, right? And next is the easy compatibility and the usability for the developer space. Just like OpenAI, vLLM also gives you the option of endpoints. You can generate endpoints similar to OpenAI and other such servers and APIs, and you can use it freely with Python, JavaScript, or any other such language. We'll see that in the demo in the later stages, right? So just to reiterate, these four features are there, which are provided by the vLLMs. Now, before we dive into the demo, I want to again stress upon the architecture followed by the vLLM. Now, the vLLM mainly follows 3 points. The first is the model server. The model server is the core of the vLLM system. The model server simply loads the large language models into your memory and handles incoming requests from millions of users for text generation. Right? It's similar to OLlama. If you guys have used OLlama is a tool which you use in a local. But this will not work when you have to scale at enterprise level. When you want to do that, you have to use vLLM, right? The next architecture or the next important point, just like we discussed, is the paged attention algorithm. Now, paged attention algorithm is a smart memory management system which is inspired by how your regular Linux operating systems handle the virtual memory. We all have seen how swap memory or virtual memory is handled by the Linux systems, right? After some time, the memory is kind of cleaned and new or fresh tokens are created, right? Same thing happens in case of vLLM using paged attention mechanism, where it breaks the user requests or cache into smaller pages, and these pages are then served by the model for the longer text and the dynamic text, right? And then the next important point in the vLLM architecture is the continuous batching engine. Again, we discussed about this. There is a continuous need for KV batch removal system, and vLLM kind of handles that pretty gracefully by continuously keeping the batch sized enough that the GPU space are properly utilized, right? So this is the architecture. Now, moving on to the demo. What we have done here is, in case of demo, we have simply used a CPU image, not a GPU image, to showcase here. Just a minute, maybe I'll. Okay. Yes. So what I'll do is, maybe I'll check the nodes. Oh, sorry. Oh. Okay, so we have used a 3-node Kubernetes cluster here. This shows that, okay, it's a 3-node cluster. And like I said, we are using a CPU architecture here. And now if I show the pods that we have, yeah. So we have a vLLM CPU pod running here. And now let's check the service that we have. So we can do SVC. Yeah, so this is the vLLM service which we have integrated with the Kubernetes pod, and this service will act as the endpoint for you. Before we move for the prompt, I just wanted to show the code as well that we have used. Okay. Yeah. Okay. I think it's little. Okay. I hope it's visible to everyone. So here, first we have developed the Python code that is in app.py. So in this code, we have simply imported the required dependencies and modules for running our LLM model. We are using Fast API, the transformer dependency, torch model, and these are the simple dependencies for logging time and everything, right? Next, we, just like any regular Python code, we are using a CPU system here, not GPU, because there is scarcity for GPUs, right? So for the demo, we are using a CPU here. And then we have implemented a method for chat completion and prompt replies, just like we do that in OpenAI, just to showcase that these vLLMs can be replicated for multiple APIs and can be plugged to any API similar to OpenAI or Cloud API, right? And then, in the end, what we do is, in the main function, we simply run this app, and the app response will be given at the port 8000 via the Fast API endpoint, and simply we can get the results, right? Now, this is the Python code that we have developed. In the process, what we are doing is we have prepared a Docker image as well. So in this Docker image, we are simply using a slimmest version of Python 3.11 to keep it light. And we configured Python here, and then we have configured the required installs and modules. Then we have a requirement.txt file where we will pull all the required dependencies here. These are the same dependencies which we have imported in the app.py file, right? And then coming back to the Docker file here, yes. And then we are exposing this endpoint via port number 8000. And then we have implemented a probe also for health checking, just to check if the vLLM cluster is running fine or not, right? This Docker image, we have pushed it to the Docker Hub. Now, I'm not going to pull it again because it's going to take too much time. It's a huge Docker image of more than 2 or 3 GBs. So I have configured this in local also. In the local system again, what I have used here is, it's a simple vLLM CPU-based configuration where we are pulling ChatGPT. Okay. So this is the same code that we have used in Python. So just to keep it simple, I copied the same exact code in my arguments. This will be when I call the endpoint, this code will be triggered and it will give me the replies, right? And then a simple service for health check, another service for load balancing and high performance. So these are the services that we have used here. If I show you the high performance service, this is the service that we have used here for horizontally scaling the production server or pods. This will help you when we have millions of requests coming in, right? Whenever we have a spike, when we see a spike, automatically it will scale up. When the spike comes down, it will scale down, right? That's the beauty about Kubernetes, right? Similarly, we have another service where we have implemented a load balancer. This also will help to load balance the load on the GPUs. And then after this, we simply deploy it, and we are using a fast API to get our responses. We can use the endpoint, which is exposed on port number 8000 for the responses. Right? Now, going back to the demo once again. Okay, so we saw that we have a 3-node cluster. On top of that, we have configured a node, which is having the load balancing service enabled on it, and a high-performance vLLM system running on it. Now, we have used a GPT model just for the demo. We can use any model here. We can pull the DeepSeek model or Gemini or any other open source model to scale it on vLLM and in Kubernetes, right? Now here, if I ask a question, we will get the result from yeah. So I have kept the question prepared just to save myself from writing during the demo. So what we are doing is we are simply running a curl command, which will do a post request on the IP which we have configured with the Kubernetes and pods. And here we are trying to do a chat completion where we will simply ask a question to GPT-2, which we have deployed in the vLLM server, and we'll get the response. So I just ask what is Kubernetes, right? And again, also, just like OpenAI API, we have configured the number of tokens and a temperature also, right? Now, this response we are getting from the vLLM server that we have deployed. So we asked about what is Kubernetes, and you can see it is telling that it is a new service and it needs to be deployed on large scale. Since it is GPT-2, an older model, so that's why the answer is not that framed properly. Now we have GPT-4 and 5 also in the picture, but for CPUs, GPT-2 will work, but we can run GPT-4 and GPT-5 and these models on GPUs as well, right? So that's the demo. And this is not just the end of it. This is just the starting. vLLM is just 1.5 years old. It's again graduated, and there are so many open and pull requests which are open in the GitHub. And we are looking for the contributors there who can contribute and help with the code and fix the PRs and all those things, right? Also, along with that, the vLLM system, again, is preparing itself for the new versions of models which are coming up so that it is multimodal in nature. Right now, also, it's multimodal in nature. But as we all know that daily new models are coming up, right? So to enable all these models, to be able to pull all these models in the vLLM system, we need the proper configuration which can connect to these new models, right? So I think the scope of improvement is huge, and we all need the support and the developer support from everyone. Yeah.
Yeah. Thank you very much for attending a talk. Yeah.